everyone, and welcome to this episode of Net Ionic Equations. Today we're going to be doing some reactions that are not necessarily precipitation reactions, as in our previous episodes, but the same rules still apply when gases and liquids and other things are formed. So let's get started. First, I have some copper 2 sulfate solution, which I will be putting into this test tube. There we go. Next, I have a strip of zinc metal, which I'm going to drop into the copper sulfate solution. This, if all goes according to plan, should do a single replacement reaction where the zinc replaces the copper, which is already in the compound. Now, single replacement reactions take a little while, so we're just going to have to let it sit maybe over here in this little test tubey thing. In this reaction, I started with some solid zinc and some aqueous copper sulfate. And the products here are aqueous zinc sulfate and some solid copper, which was the brown stuff forming on the surface of the metal. To make the complete ionic equation, I broke up the aqueous copper sulfate into its two ions. Again, note that I showed the charges. And the zinc sulfate also was broken up into its ions with their charges. The zinc started out as a solid, and we ended up with copper solid over here. So in this reaction, I really only had one spectator ion that started by itself and ended by itself. That was the sulfate ion. So I omitted that down here. But it also looks, at first glance, like the copper and zinc also started by themselves and ended by themselves. However, they did undergo a very important change. Zinc started out as the solid element with 0 charge, but ended up as an aqueous ion with a 2+ charge. So it must have lost 2 electrons along the way. And so that is a change that I need to report. The solid became the aqueous. And the copper did the opposite, started out aqueous and ended up solid, because it gained 2 electrons, those 2 electrons that were lost from the zincs. So my net ionic equation is solid zinc reacting with aqueous copper 2+ ion to make zinc ion and some copper solid. For reaction number 2, I have some sodium carbonate. You can see that it's a solid white powder that I put inside this lovely Erlenmeyer flasky thing. We're gonna add some hydrochloric acid to this sodium carbonate, and we'll see what happens when the hydrochloric acid goes in. Here we go. And yes, definitely a chemical reaction happening there. You see some bubbles forming that weren't there before. And some of my white solid has dissolved. Let's add a little bit more. See if we can get all of that to dissolve. And we'll just add a bunch. Why not, right? Here we can see the last little bit of sodium carbonate trying to dissolve, and we see a little stream of bubbles coming up from there. And our job here is to communicate what are those bubbles and what is the reaction that's actually happening here. As always, when you write a net ionic equation, you want to include all the things that actually reacted and changed during the reaction, and you want to omit all of the spectator ions, the things that remained aqueous before and after and didn't really get together with anybody and didn't change. In this reaction, I started with some solid sodium carbonate and some aqueous hydrochloric acid, and my products were aqueous sodium chloride, some liquid water, and gaseous carbon dioxide. Those were the little bubbles that we saw. For the complete ionic equation, I split up both of the aqueous compounds. This was a solid, so I did not break it up. It actually was together when I started, and the hydrochloric acid was split up, and the sodium chloride were also split up. The water, which is a liquid, that's a pure the water which was liquid, we left together, and the carbon dioxide gas, which were those bubbles, also stayed together. In this reaction, there really only was one spectator ion, and that was the chloride ions. There's 2 of them that started by themselves and ended up by themselves, and so we got rid of them. Everything else actually changed during the reaction. The sodium started out as a solid and ended up aqueous. The hydrogen ions started aqueous and ended up in a liquid. The carbonate started out with 3 oxygens and ended up with 2 oxygens. One of those oxygens went over to the hydrogen to make the water. And so everything that remains actually changed during the reaction. So I left it all down here in my net ionic equation. The only thing I omitted was the chloride ions. I'm going to start with this wire. I'm going to find the mass of it first, and then I'm going to dissolve it. This right here is concentrated nitric acid. It's almost 16 moles per liter. What that means is it's really scary. Like, you really don't want to make it angry. You want to talk nicely to it, treat it with respect, otherwise bad things happen. I'm gonna get this party started by pouring some of the nitric acid onto my copper wire. Just a little bit is all we need. All right, so we've got the copper wire in the nitric acid. I see some bubbling happening there, and you can maybe see this brown gas that's being produced. That is nitrogen dioxide gas. It's one of the products of this reaction. Oh, now it's really getting going. And you can see the solution at the bottom is turning green because that's the copper dissolving into the solution. Let's all enjoy that for just a second. This reaction has to be done in the fume hood for obvious reasons. This brown gas that's produced, we don't want to be breathing that. That is nitrogen dioxide, which is one of the main components of smog. And if you've ever been in a very smoggy area, you know what I'm talking about. So I'm going to let this go until it's finished. Before I leave the fume hood, I want to kill the reaction by adding a bunch of distilled water. So I'm going to go get that while this finishes up. Back in a sec. In the reaction we just saw, the solid copper went into the aqueous nitric acid and produced some aqueous copper nitrate that turned the solution green and then blue. And then we have a brown gas, nitrogen dioxide, and some liquid water that was also made. Now that we've got the complete chemical equation, feel free to take a moment, pause the video, and write out the complete ionic equation and the net ionic equation. If you were able to correctly deduce that you have to get rid of some but not all of the nitrate ions to make a net ionic equation, then congratulations, you're doing an excellent job. For the complete ionic equation, I split apart the nitric acid and the copper nitrate. Nitric acid is a strong acid, so it's going to be 100% dissociated, and copper nitrate is soluble, and so we separate those. So we get copper solid, 4 hydrogen ions, 4 nitrate ions, 1 copper 2+ ion, 2 nitrate ions, and NO2 gas and H2O, which is a liquid, and we're going to keep those together. And then things get a little tricky for the net ionic equation, so if you're able to navigate that, congratulations. We have 4 nitrates on the left and only 2 nitrates on the right. So 2 of the nitrates didn't do anything. They started up by themselves and those 2 ended up by themselves. And so we got rid of 2 of them. But there were 4 to begin with. 2 of them then went on and made the NO2 gas, the brown gas that we saw. And so those 2 actually changed. So I'm going to keep those in the mix, but I'm just going to get rid of the 2 nitrates that didn't do anything. And there you have our net ionic equation. Copper plus 4 hydrogens, 2 nitrates makes a copper 2+ ion, 2 NO2 gases, and 2 water molecules. The 3 reactions in today's episode were not precipitation reactions, but even though there were no precipitates formed in today's reactions, the ideas are the same. You want to split apart anything that's soluble and then cancel out any spectator ions that stay soluble both before and after, but include anything else that does change, whether it goes from a solid to aqueous, solid to liquid, liquid to gas. Look for those changes and include those in your net ionic equations. And that's it for this time. So thanks for watching and happy equation balancing.